Today I will talk about my PhD study. Most of the results is from in these structures. Then I'll finish my presentation, giving a summary and conclusions of my research. Gallium nitride has excellent properties in mechanical and electrical and optical means. Since it's a very good material, it is being used in optical electronics like large-scale displays, wide LED generation, optical storage like Blu-ray LEDs, or even in traffic lights nowadays. Gallium nitride has two different crystal structures. One of them is word-side crystal, word-side crystal structure. It is hexagonal vortex structure. It has a bandgap energy of 3.42 eV at room temperature. The other crystal structure is zinc blende cubic structure. It has different bandgaps at 3.20 eV at room temperature. It has a large extern binding energy in bulk. It is 25 MeV, which is very close to room temperature thermal energy. Extern is a quasi-state of electron and hole, which are attracted to each other by Coulomb interaction, and they freely move in this structure in the crystal, which is very important for efficient light emitting diodes. And its binding energy increases till 40 MeV when we do two-dimensional structure like quantum loss, and also have very well developed growth technology. In the right-hand side image, you see energy bandgap versus implant lattice constant for three nitride alloys: aluminum nitride, gallium nitride, and indium nitride. These have all a word-side crystal structure which is evolved, which the technologies evolved in this structure. And as you see, along these semiconductors, we can easily cover visible spectrum. And we do indium gallium nitride for blue light emitting applications. However, there are problems associated with active regions used in LEDs and lasers. This is in the right-hand side image. You see a normalized quantum efficiency versus injected carrier density. The problem with the LEDs is efficiency loss at high excitation levels, at high injected current densities. The blue curve shows without efficiency loss for an LED active region. The red one is the efficiency loss with quantum efficiency, with efficiency loss. Our goal was to improve or mitigate this efficiency loss problem and get very good quantum efficiency LEDs. And the left-hand side image, you see a flat band concentration of an active region from an LED. This is N side, this is P side, this is multiple quantum, indium gallium nitride multiple quantum wells, which has smaller bandgap compared to gallium nitride. Efficiency loss has problems. These are caused by Okur recombination, I'll talk about later, or electron current leakage, poor hole injection efficiency, and non-uniform distribution of carriers. I will talk about this later. In the left-hand side image, you see the carriers are injected from the N side. However, not all of the carriers are contributing to radiative recombination. Some of them are overcrossing the active region, like contributing to the electronic current leakage. Some of them are recombining in active region. However, still, not all of them is contributing to radiative recombination. Some of them are non-radiative recombine. I'll talk about those later. The left hand side image, you see a conduction band and valence band of a semiconductor. I told you not all of them are recombining radiatively. The green arrows show the radiative recombination paths for a semiconductor, and there are acceptor and donor levels in the band gap, and there's trap levels in the band gap as well due to defects or due to different impurities. A carrier radiatively recombined through conduction band to valence band, or valence band to acceptor levels, or between donor and acceptor levels. However, the trap levels in the band gap captures the carriers and it increases the non-radiative recombination process. These are not necessarily in the mid of the energy band gap. They might be constituted in different levels in the band gap. Another process is Auger recombination. The energy is transferred to another carrier in the conduction band, and this energy, this electron is transferred to upper levels. So this process, instead of giving light, those energies used for transfer another carrier. This is another non-radiative process. This is effective at high excitation levels, at high injected current densities. Extons, as I told you, play an important role. However, those might be in free exton mode without bound to another structure in the crystal, or exton might bound to donors in crystal, or it may bound to structural defects. Those has different energy levels, as you see, and they constitute different energy levels and transition in the middle of the band gap. In the band gap, this is the conduction band, this is the valence band. As I told you, our goal was to mitigate this efficiency loss problem, and we had several solutions for those. This is a very simplistic active region for an LED. This is a flat band constellation, as I told you earlier. In reality, in the polar directions, we have a polarization fields which bends this structure. The problems were the electron leakage or high Auger recombination process. We want to mitigate this problem by by engineering the band structure. As I told you, we had non-uniform carrier distribution in active region. This is 2 nanometer quantum wells. This is 15% indium galvanite, right? Emitting around 430 nanometer. And these are the barriers. With this 1%, it may change. And we thought we may increase the thickness of the active region to change the carrier density in the active region to decrease the efficiency loss problem. When we change this quantum loss from 2 nanometer to 3, 4 to 10 nanometer, it is called double heterostructure active region, and it has 3-dimensional density of states. This helps to increase the optical output from an LED, and since this has 3-dimensional density of states, it decreases the Auger recombination process, so it helps to mitigate this problem. Another way to mitigate this problem was adding an aluminum diamide electron blocking layer. As I told you earlier, electrons were overcrossing the active region. We can create an effective potential, and the number of the carriers in the active region would increase. Another way to use a staircase electron injector. This is a stepwise decrease in indium composition layers with different thicknesses. As you see, this is 4% indium, this is 8% indium, and we can investigate this thickness, the effectivity of their thicknesses. This is acting an electron cooler. As I told you, these injected carriers has high kinetic energy. When we decrease this indium composition in great levels, we will promote LO phonon emission, LO longitudinal optical phonon emission, so we can cool down the gain kinetic energy with these injected carriers. Or we can change the quantum, this barrier thicknesses very high also to increase the distribution of carriers in the quantum wells, so we can obtain more, we can reach higher optical output. So now I will talk about the results of my research for the first topic, quantum efficiency of INGAN active regions. Before that, I will show you the optical setup that I used to investigate the optical efficiency, quantum efficiency of these structures. We use tight-sapphire tunable laser, which is pumped with a NDO solid-state laser. It is 532 green laser, and we can tune tight-sapphire laser between 700 and 1000 nanometer. We use a doubler tripler, which has a non-neri crystal inside, and it doubles the frequency of the light, which is needed to resonantly excite the quantum wells. This is 400 nanometer. If we use 800 nanometer laser and sample is mounted in a cryostat, so we can change the temperature. We use 400 nanometer excitation because 15% indium diameter quantum wells are 430 nanometer, and we can, so using this 400 nanometer laser, we will not excite the barriers or staircase injected layers. So our goal was to investigate only the quantum wells. So the collected information, photoluminescence, is sent to a spectrometer to analyze the photoluminescence. It can be either analyzed using a streak camera or CCD camera. Streak camera gives us how fast these carriers recombine, and CCD camera gives us intensity information of this photoluminescence. And we can also change the detection to investigate other optical properties. We can also use polarizer to investigate the polarization direction or degree of polarization of this photoluminescence. Or we can also use electro-optical modulator, which is another non-linear process to change the repetition rate of this tight-sapphire laser. This is due to the carriers which are recombining longer, like 2-3 nanosecond range. If we change the repetition rate, we can see long-lived carriers, like 10 nanosecond, 20 nanosecond radiative combined carriers. Now, as I told you earlier, the thickness of the active region was important. We changed the active region thickness from 3 nanometer to 11 nanometer, and we doubled those active regions, dual 3 and dual 6 nanometer, and we did internal quantum efficiency measurements. These measurements are obtained using temperature dependent photoluminescence measurements and excitation density dependent photoluminescence measurements. The top, the maximum levels are obtained comparing by just 15K and room temperature levels, and the internal quantum efficiency is obtained using excitation dependent measurements. Internal quantum efficiency is a measure of how many carriers are effectively involved in radiative recombination. As I told you earlier, there are non-radiative processes in active region. This is a measure of how efficient is the active region. As we see in the left-hand side of internal quantum efficiency, we saw that 3 nanometer and dual 3 nanometer has highest internal quantum efficiency compared to other active region thicknesses. This is due to increasing the thickness of the active region. The quality, crystal qualities decreases, so it increases the non-radiative centers. So we thought this is the best. For that reason, 3 nanometer and dual 3 nanometer has better efficiency. And in the right-hand side image, you see relative external quantum efficiency results. This is basically the intensity of electroluminescence versus current density. As I told you earlier, the problem was the efficiency loss. As you see from 6 nanometer and dual 6 nanometer, we clearly see efficiency loss at high current densities. However, at 3 nanometer and dual 3 nanometer, we see a lower, or we can say lower efficiency loss. However, when we increase 9 and 11 nanometer, they have a low efficiency loss too. However, their optical output is lower, as you see, compared to dual 3 at the 6 nanometer active region. It has higher EL output compared to 11 nanometer quantum level. Since single and dual 3 has good optical output, we said we can increase the number of these layers, double structure layers, to obtain higher photoluminescence or higher PL efficiency. We increased these 3 nanometer 2 by 3s, 4 by 3, 6 by 3, and 8 by 3 nanometer double structure active regions, and we saw that we see the best performance for hex 3 nanometer, 6 by 3 nanometer double structure active region. In the explaining this, as I told you, we are doing band engineering. We used staircase electron injectors to cool carriers which has higher kinetic energy. We investigate the SEI thickness, staircase electron injector thicknesses, to see if we can reduce the electron current leakage from these active regions. And in the active region, we used no SEI, without SEI, single 3 nanometer DH plus 4 nanometer SEI. This is the thickness of SEI layer, as you remember, 4 nanometer, 8 nanometer layers. And we increased to 20 plus 20 nanometer and 30 plus 30 nanometer SEI, and we saw that there is a significant difference with increasing the SEI thickness. And we found that we can only increase these layer thicknesses to some level. So it was the 20 plus 20 nanometer SEI layer, and we see that This is the best design, 6x3 plus 20 plus 20 nanometer ACI layer. We also investigated carrier dynamics in active regions in order to improve the quality of these active regions. And I used three different active regions. One is 6 by 1.5 nanometer, the other 6 by 2 nanometer, the other was 6 by 3 nanometer active region. This is PL intensity, this is the time, decay time, this is the time passing for the carriers recombine. At this level, this is the excitation is given, and since this has a 150 femtosecond laser, if the lasers at this point the excitation is removed, then the carriers started to recombine from this. And as you see, for different structure, we have different transit, we have different profiles. If we do temperature dependent photoluminescence, and if we do temperature dependent time result photoluminescence measurements, fitting this, we can obtain PL lifetimes. So comparing these results, we can obtain radiative time constant. So this is showing the comparison of radiative lifetime with non-radiative lifetime, and since we obtained photoluminescence lifetime, this experimental value, comparing temperature-dependent photoluminescence and PL lifetimes, we obtained radiative lifetimes and non-radiative lifetimes, and we saw that at low temperature, radiative lifetime is dominant for photoluminescence. At room temperature, we saw that non-radiative lifetime is effective for photoluminescence. And comparing these structures, since these were 1.5 and 2 nanometer, these were close to two-dimensional structure, and we clearly see that from the temperature dependence, it has really a two-dimensional structure, which has the dependence on one with radiative decay time versus temperature. However, 3 nanometer has different dependence. It was 1.5. It is very well fitting with the theory.
How do you extract the non-radiative?
How do you
extract the information about non-radiative lifetime?
We extract like this in sorry. You see, we obtain PL lifetimes by just fitting these curves. The information is here. The 1 over tau PL is dependent on 1 over tau radiative and 1 over tau non-radiative. If we do temperature dependence photoluminescence measures, we can obtain the intensity. So we can plug here. We can use these two information in order to obtain radiative lifetime. Since we know this information from fitting, we can just plug here. We can obtain non-radiative lifetimes too. However, one condition here, we say that at low temperature, the non-radiative centers are not involved in processes mostly. However, this is very well fitting with the theory and application.
Last equation is your from last equation.
Yeah, from last equation we just obtained. If we summarize this section, we can say that we can use 6 by 3 plus 20 nanometer ACI layer for best efficient LED active region, which we can use in vertical cavities. From carrier recombination dynamics, we see that radiative recombination is dominant at low temperatures. However, non-radiative is dominant at room temperature. Now I will talk about the optical efficiency and carrier dynamics in non-polar and semi-polar gallium nitride directions, which earlier was in polar directions. This is the polar C-plane direction, and this is M-plane non-polar direction, and this is another M-plane, A-plane non-polar direction in vertex hexagonal structure. There are different semi-polar directions. This is one of them, which is shown in light blue. And the right-hand side image, we see a comparison of active region of polar and non-polar directions. As I told you, there's a polarization in polar directions, and which is bending the energy bands. Here it is shown. This is reducing the electron and hole wave functions overlap. As you see here, this is electron wave function in conduction band. This is hole wave function in valence band. The efficiency of radiative recombination decreases since these carriers are not seeing each other. However, in non-polar directions, this is M-plane direction, there is no polarization fields, and electrons and holes are recombining radiatively, and the overlap of electron and hole wave function increases. So, in order to increase the efficiency, we wanted to use these directions. We wanted to grow active regions on these directions. And the left-hand side image, you see non-polar and semi-polar direction. This is one bar 01 direction which we used in active regions. This is a process how we grow semi-polar LEDs. Instead of sapphire substrates, which is commonly used in polar directions, we use silicon substrate, and we use etching techniques, acid etching and dry etching techniques, and we grow end-plane structures for these substrates. We used M-plane non-polar gallium nitride, and 1 is gallium nitride substrates, and compared PL efficiency and time resolved photoluminescence in order to compare the quality, and we found that 1 has a PL which is close to a state-of-art C-plane gallium nitride substrate. For that reason, we wanted to investigate more this semi-polar gallium nitride substrates, which we use two different silicon substrates, which has different traces to obtain film like coalesced semi-polar film. This surface is 1 and this direction is the growth direction. It is C-plane direction 0001, basal plane gallium nitride direction. And we also obtained non-coalesced layers, and we compared times of photoluminescence to see which one is efficient, and we found that this non-coalesced layer has 1.15 nanosecond PL decay time, which is longer than a nano-yellow, that is another name of technique to get polar gallium nitride on sapphire substrate, and this semi-polar structure has better efficiency compared to polar gallium nitride substrates. Also, coalesced layer. This coalescent, we found that increased the density of extended and point defects in substrates. So maybe I should show you here when we grow this sapphire, substrates. It grows in this direction and in this direction and other directions too, and we call that this is C plus side, and this is C minus side in this polyester film. So we want to investigate the spatial quality of these layers. And we used microoptic, which has about 2 micrometer spot size, to see which layer has better efficiency. And we found that the initial decay time of from transients, we found that this C plus side has a longer decay time compared to C minus side. This is an indication of higher quality of C plus sides, and we have further investigated those using near-field scanning optical microscopy, also using cathodoluminescence measurements. In the left-hand side image, you see an AFM image, and this is a correlation of photoluminescence from this surface. These are 13 micrometer rings, non-coalesced layers, and this is the C minus sides and C plus sides. And we see that the source of photoluminescence is coming from C plus sides instead of C minus sides, which is correlating very well with the time-resolved photoluminescence measurements. We see that it has higher threading dislocations and defects in C minus sides, and cathodoluminescence measurements are very well correlating with these photoluminescence measurements. This near-field scanning optical microscopy, you can just think a film which is attached to an optical fiber which has a different diameter. So we used here 100 nanometer optical fibers to see these structures. And we did cross-sectional cathodoluminescence measurements, and we found that C minus side has really has higher density of threading dislocations, and this is free of extended defects. We found that in this the touching points to silicon increases the basal stacking force in the structure. However, in the growth directions, it is always usually see a threading dislocation in growth directions. This is C plus directions. However, when they grow, this threading dislocations bends towards the surface when they meet with semipolar fronts. So this is the dot lines are the growth process. When threading dislocations meet with this semipolar direction, they just bend towards threading the surface in that direction to minimize the efficiency. So to minimize the energy. And we grow LED structures on these active regions, and we found that still correlating with the substrate. And this is with the reflection image of the source of photoluminescence from these structures. And in the left-hand side image, the comparison of photoluminescence of polar C-plane LED and semipolar 1 LED used same active region and grown in the same process. We see that semipolar has a higher indium incorporation in the active region. However, their photoluminescence, the intensity is similar to each other. So this is very promising to use these structures in light emitting applications. So if we summarize this section, we can say that semipolar 1 substrates as well as Indian active regions are very promising for future distributed Bragg reflectors and active region. Active region is sandwiched between these distributed Bragg reflectors. Distributed Bragg reflectors are lambda over 4 thick alternating layers which has their refractive index difference gives a broad reflectivity band. I will show those later. For an in active region, an aluminum nitride, gallium nitride distributed Bragg reflectors is a natural choice because we can naturally grow active regions on this distributed Bragg reflectors. However, there are problems associated with aluminum nitride, gallium nitride distributed Bragg reflectors. Since this has small refractive index difference, we need to grow higher number of aluminum nitride, gallium nitride distributed Bragg reflectors compared to silicon nitride, silicon dioxide distributed Bragg reflectors, which has higher refractive index difference. Also, since we need to grow higher number of pairs, the crack in the layers is increasing, and this is decreasing the quality of vertical cavity structure. So in order to obtain higher output, also we need to place the active regions in the antinodes of electric field in the microcavity. Now I will show you optical results which I obtained from that vertical cavity structure. This is the bottom DBR reflectivity, which you see it is 18 to 20 nanometers stop band, which was designed at 410, and this is the full cavity reflectivity from the silicon nitride, silicon dioxide DBR. This has 13 pairs of aluminum nitride, gallium nitride. However, this is only this is 30. This is 13 pairs. This is 13 pairs, 3 pairs only. So we can obtain larger stop band and higher reflectivity compared to aluminum nitride, gallium nitride DBR. Since there is a non-uniformity, we can shift this aluminum nitride, gallium nitride DBR. It is difficult to obtain the cavity conditions. This is the photoluminescence which we obtained from this cavity. It has high Q factor, 1300 Q factor of from cavity structure. Q factor is the designed wavelength versus the full width of half maximum. This, however, not all of the sample is everything in this way because of non-uniformity of aluminum nitride, gallium nitride DBRs. So our goal was to use dielectric DBRs, which was easier and which has better performance compared to aluminum nitride, gallium nitride. However, in the field, they have to remove the substrate in order to deposit second aluminum nitride, the second silicon nitride, silicon dioxide distributed Bragg reflectors. I say silicon nitride, silicon dioxide. However, there are different dielectric materials which are used in these cavity structures. We proposed a way to use not to remove this substrate process. It is called abduction lateral overgrowth technique. Basically, what we do is we have separate substrate. We grow first gallium nitride, which has a trading dislocation density of 10 to 9, 10 to 10. Then we use masks. These masks are silicon nitride, silicon dioxide masks, and we process and we open these openings. Then we again grow gallium nitride using MOCVD technique. These wings, when we grow gallium nitride, it grows in this direction and this direction too. However, these masks prevents the trading dislocation motion, so we obtain defect-free gallium nitride layers, which has better performance. So we can grow active regions on this defect-free defect-free gallium nitride substrates. So we can also implement both dielectric DBRs. So we can also, using this technique, eliminate the substrate removal process. Left-hand side image is showing SEM image, and this is the grown yellow layers. This is sapphire substrate. This is first gallium nitride layer, and this is this layer. This is bottom dielectric DBR instead of DBR deposition. This is the optical performance for this full cavity structure. This is the reflectivity measurements from the full cavity structure, showing a cavity modes, leaking cavity modes, which is showing a good quality of vertical cavity structure. In the right hand side image, we see a photoluminescence results from only active region, which has a Q factor of 20. This is without distributed Bragg reflectors. This is half cavity, it is only the bottom dielectric DBR. When we complete the full cavity, we increase the quality factors of 500, which is showing the good quality in these layers. If we summarize this section, we say that all dielectric DBRs, all means bottom and top dielectric distributed Bragg reflector vertical cavity, we can say that we reach high quality of in active region, since this yellow has defect-free gallium nitride substrate. Also, we integrate the dielectric bottom dielectric DBRs for the into the vertical cavity structures, which helps us to eliminate the need for the substrate removal. For the last words, I can say that my investigations are mostly related to blue optoelectronic devices like LEDs and vertical cavity structures, and I investigated active regions which I used in these optoelectronic devices, and we see that we can mitigate the efficiency loss problem and implement this into these light emitting applications. Thank you very much for attending my presentation. If any question comes.
So what is the dependence of the lattice mismatch, which depends on the indium content, where you show this in the multiple quantum well structure, for example?
You say dependence of lattice mismatch, indium nitride and gallium nitride, right?
Indium gallium nitride.
The problems mean 430 nanometer. This 15% indium composition is now good quality, which has lower density of dislocations. However, when we increase to 30%, the problem starts, and the indium clustering starts in the active regions, which has deteriorating the quality and optical quality especially. So for that reason, we just stick 15% indium composition, and we always shoot there to improve the active region quality. I mean, for the lattice mismatch, indium nitride and gallium nitride has specific in-plane lattice constants, so the technology is developed in that way, so we can efficiently use 15% indium nitride.
Because I assume if you make the quantum well thinner, the lattice mismatch should play more role in the. It might create surface states in the interface states.
That might be, but however, the thicknesses we use, we don't see those problems. So we use different thick layers, like in 2 nanometer, 1.5 nanometer wells. So when we use 15% in our MOC, we always get what we wanted. So
So how can you make sure that you don't create super lattice instead of multiple quantum well there? Because the confinement is so high if you make the quantum well thinner, right?
Yes.
So
what we do is.
So there should be intertunneling between the neighboring, the adjacent, right?
Yeah.
The quantum wells, so you end up with super lattice.
The electron and hole wave function over them. So it is gonna, of course, it depends on the quantum well, also quantum barrier, how thick we use. We use 12 nanometer thick quantum barriers, or 3 nanometer quantum barriers. It is also, we changed the composition of these barriers, and we found that 6% quantum barriers with 3 nanometer thick was the best design for higher light output. This was the goal. So that is what we get.
But it's amazing to have bound states
Yeah.
for 3 nanometer, 2 nanometer thin quantum well, right?
Yes,
I mean,
exactly.
I expect some leakages, right, for upper levels.
That might be true. However, for the efficiency loss, those all are combining into. Those are all in the picture, So, however, we just specifically select. This is our problem. We wanted to eliminate that problem. For that reason, we use algan barriers or staircase electron injectors. So. That there might be another problems. However, which one you focus, that's the important, right? So that's what we do. We just select our problem and shoot it. That's it.
Thank you.
Welcome. I hope we can fix this problem.
Can I ask another question? How do you mean by semipolar? I mean, how is this polar? Is it the surface polarity? Due to the surface states, empty and field states of, or is it something different? Because I never heard the term semipolar for surface states. It's either polar or non-polar surface, right?
Yes. However, depends on the growth method. You can obtain semipolar surfaces too. So, for example, what we use, in order to obtain non-polar gallium nitride, we use silicon 111 substrate. In order to obtain semipolar gallium nitride, we use silicon 001 substrate. That might be vice versa, but we can check. As I shown before, it is how you etch this substrate, so you can obtain different surfaces, some semipolar surfaces too. It might be 11 bar 01 or 112 bar 2. For example, we also used M-plane sapphire substrate. When you just directly grow on M-plane sapphire, I might be wrong. Yeah, it is M-plane sapphire. You can obtain 2 bar 2 gallium nitride. It is semipolar too. You don't need to trace the substrate, silicon substrate. So you can obtain. This is related to the polarity of those crystal structures, as I told you earlier.
So when you change the size of your wells or the number of your wells, doesn't the emission wavelength change by a lot? Is it still blue lights? Or
Yeah,
you have to
maybe
compensate?
in the 11 bar 01 LED, you saw that we use same active region in the same conditions. However, we obtained for one semipolar, it was 450 nanometer. For the other one, it was 430 nanometer. Both are in blue. However, there is a shift because of the more Indian incorporation in the semipolar direction. So both are blue. It is not green, so it has to shoot above 500 in order to get green. So, however, still we are in the safe place to obtain blue emitting lasers or LEDs for those different
surfaces.
Any other questions?